Today I want to talk about specifically generative AI in 3D and how it sort of all started. Obviously if you keep up with AI, there's been large language models for text, 2D diffusion for images and video diffusion for videos, but there's not been that one big sort of model for 3D. It's been a bit slower on that end. So what I want to talk about is how we can generate objects in 3D and why it's a lot harder to do it in 3D than it is to do it in 2D. If we're going to talk about 3D object generation, we need to talk about 2D first. So 2D is all done using something called diffusion, which you've probably heard before. But for those who haven't, I'm just going to do a quick recap. You give it an image prompt. So for this, I'm going to do frogs on stilts, which is what I've been doing for the past few videos. It's based on Mike's prompt from his amazing video about 2D diffusion. So if you don't understand this, I recommend going and watching that.
Frogs on stilts. I'll have to try that later.
I'm looking forward to this.
So what you do is you have an image that is complete noise, okay, random values in there. And what you do is you give that to a diffusion model with your prompt. And that diffusion model goes, okay, if you want an image that looks like frogs on stilts, you need to take away this amount of noise from that image. You'll start getting an image that starts looking a little bit like a frog on stilts. So what happens is that at time step t equals 0, you'll have complete noise. And then you pass that through the diffusion model several times. And then let's say this is now t equals 10. So you've done it 10 times. You'll start getting a frog on stilts like that. Oh God, I've run out of space. But at t equals, let's say 20, you'll have your frog on stilts. So here's the thing with 2D diffusion models, which is just so cool, is the fact that they can merge these different concepts. So you have a frog and you have stilts. Never the twain shall meet. There's no photo that exists in real life. Well, maybe there is. Someone's probably done some abstract, some abstract stuff with that. But it's just those two concepts couldn't be further apart, but they're able to join together. And the reason for that is that these 2D image diffusion models are trained on billions and billions of image caption data. So these training sets are absolutely massive. And that's how they're able to learn how to draw a frog very well, how to draw stilts very well, and put them together. 3D is more tricky. So in 3D datasets, I think the largest one has around a couple of million. If you want to generate a frog on stilts, what you'll find is that there aren't that many frogs in the dataset, and there aren't that many stilts in the dataset. So when you ask it to generate a frog on stilts, it can't really do it that well. So that's the first problem, is that the datasets are smaller. The second problem is that 3D is just so much harder than 2D because you've got to think about every single angle. So it has to look good from every angle and it has to look realistic, which a lot of this 3D data it doesn't look as real as real life. Anyway, that's the problem with 3D data. How do we solve it? So just to preface, these days there are some 3D generation models that just work on 3D data. Mesh GPT is a good one if you want to have a look at that. But in general, it's still early days for that sort of thing. But what has happened in 2022, there was a model called Diffusion that came out. And this model was it was groundbreaking because it was the first time that 2D diffusion was used to generate 3D models. So as I say, 2D diffusion models are very, very good at making abstract concepts like frogs on stilts. So we want to use that to generate 3D content. So Diffusion was the first model that came out that did that, and it was revolutionary because what they did is they leveraged 2D diffusion and projected it into 3D. So we're able to get these abstract concepts like a frog on stilts in 3 dimensions. And this came out like 3 years ago. So, and that wasn't long after 2D diffusion came out. So it was quite a big thing. So we have 2D diffusion models. So that stuff like stable diffusion is used for that because it's quick, it's nice, generates good images. For the 3D representation, we don't use a mesh we use a view synthesis model. Now, a view synthesis model is something like neural radiance fields, which we've spoken about.
Oh, NURFs was that?
NURFs, which we've spoken about on this channel, and now the latest sort of craze, 3D Gaussian splatting, which is my favourite thing ever. But what these models can do is you give it a series of 2D images, and they're able to reconstruct the scene in 3D via some optimization. So 2D to 3D, are you starting to sense a pattern here? So we have diffusion that can generate 2D images of what we want, and then we have Gaussian splatting or NURF that can generate a 3D model based on 2D. Right, so we have these two things, let's put them together. And how they put them together is using something called score distillation sampling. You have your prompts, I'm going to do frog on stilts. And what you do is you start off with a blank 3D scene. For Gaussian splatting, we have to initialize it with some Gaussians, but for NURF, we don't need to. Actually, to preface, I'm just going to talk about Gaussian splatting for this one because that's what people use more now, but Dream Fusion used NURF. So you have a blank scene here. So what you then do is you render a 2D image from a perspective. So I'm going to draw a camera there, for example. So that camera has rendered this image here. Okay, so what we then do is we need to add some noise to it, as we've done with 2D diffusion when you added noise to that. So this image is slightly noised up. Then what you do is you pass this into the diffusion model with your prompt and say, if I'm going to denoise this image to make it look like frogs on stilts, what noise do I need? And the diffusion model goes, you need this amount of noise. You then take it away from that image. And what happens is that that image will start to look like a frog. And then what you do is you use that image and optimize that 3D scene as if you were using 3D reconstruction, basically. And then what you find is that this scene starts to look a bit more like a frog. What happens in real life is that you do this many, many, many times. But for now, I've drawn, let's just do a really noisy frog. There you go, that explains it. So you've done it once, and now that there's a frog, that when you render from this camera angle here, it starts to look a bit more like a frog. But what you do now is you take a different camera angle. You have your camera here, and then what you do is you render a new image from here, and now you start having this frog, very noisy frog in this image. You add some noise to it. Ask the diffusion model, what would this frog look like if I'm going to make it look better? It then generates what that frog look like, what should look like from that angle, and then you optimize it, and suddenly, let's say, I don't know, this frog now has eyes from that camera angle. And so what you do is you do that again with another camera angle, again with another camera angle, again and again and again. And that's why it's called score distillation sampling, because you're distilling that sort of update over many, many camera angles and do that many, many, many times. And what happens is that you start getting a 3D model of a frog on stilts.
So each of that noisy frog is being made out of Gaussians, is it?
Yes, yes. So this is all Gaussians, or if you're using NURF, it will just be a neural network. But essentially,
splats of colour or whatever.
Splats of colour that make up a frog. Which is it's quite nice, isn't it? It's quite cool. But yes, essentially you start off with nothing, or if it's Gaussian splat, you need to initialize Gaussian splat. I won't get into that. But you start off with something that looks very bad, and then what you do is you use this you render an image, ask the 2D diffusion model, what should this actually look like? It generates an image of what it thinks it should look like, and then you do that. You update it to look more like that. But here's the thing: if you just did it from one camera angle, many, many, many times, what you do is you get a frog that looks great from that camera angle, but as soon as you move over, it would look completely just terrible. So what you do is you do it over many camera angles and do it so that it updates it all together and starts to look like your frog that you want. There are some issues that they found that we're just going to talk about very briefly. So there's this thing that they found, which I think is just awesome. It's called the multi-face Janus problem. Now, Janus is the Roman god with two faces, which I think is just a perfect analogy for this. So what happens is that, let's say you have your blank scene and you render an image, blah, 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 and then you ask the diffusion model to generate a frog. You ask it to generate a frog on stilts, what it will draw, and I'm really going to try and do this, but I'm probably not going to. It will draw a frog looking at the camera, because that's what it's trained on. It's trained on frogs where the frog is looking at the camera. That's what it just assumes it's going to be. But if you generate, you do the same on a camera angle like this, blah, blah, do the same. What it will generate, it will say, yes, that's what it should look like there. And what happens is that you end up with a frog with two heads. Because every single image it presumes is the dominant front-facing image. It doesn't understand that this image is over here and this image is over here. And that's how you get something called content drift as well, where from certain angles things will merge and look really weird. I'll show you all examples of this in a second. But so how did they solve this issue? Well, what they did is that they said that, right, in this 3D scene, this angle here is going to be the predominant angle. So when you then generate an image, you pass in the prompt that is converted into a clip embedding and then passed in of a frog on stilts from the front-facing camera. But then if they had one here, which is from the back, they would pass in the prompt, a frog on stilts from the back. So it would learn to generate it from the front and the back. But if you want to generate one from here, which is in between, what they did is that they had the clip embedding of a frog on stilts from the front, a clip embedding of a frog on stilts from the back, and then they'd interpolate between it. Let's say this is 0, this is 90, and this is 60. They do it so it was, let's say, 60% frog on stilts from the back and 30% or 40% frog on stilts from the front, if that makes sense. So the diffusion model would learn, okay, it's roughly this sort of what we need. So that solved or helped solve the multi-face Janus problem.
Because I was thinking of that very old pitch of modern day version of that.
It is. Yeah, that's spot on. Yeah, I'll show you some examples because it did fail and it has generated like some weird stuff. One other thing they realised as well is that if they just use the same amount of noise throughout, let's say, the first epoch to the last epoch, it wouldn't converge very well. But what they realised is that if at the start they have a lot of noise, then what happens is that the diffusion model is able to generate the weird sort of structures that it needs for a frog. So it's able to generate eyes and generate legs and stuff like that. But as you lower the noise, as the number of cameras that you generate goes on, it's able to then get that fine texture, if that makes sense. So at the start, it generates like really weird stuff, but it's just generating the overall structure. And then towards the end, it's finalising it and only adding a little bit of noise, so it's able to converge on a nice frog. So it's generated a frog. This is using Gaussian Dreamer, which is a score distillation sampling model that uses Gaussian. So if I click play, you can see that it's a frog on stilts. I wouldn't say that's super impressive, but it is a frog on stilts. If I go now, I can show you what it looked like when it was generating. This is a training process, so when it starts off, it doesn't really look like a frog on stilts that much, but as you go on, we're on 1000 now, and finally 2000, you get your final finished frog. So that looks okay, it doesn't look too bad. But now I'm going to show you something that doesn't work so much, and this is quite funny actually, hopefully people will laugh at it. Here we have a frog that doesn't quite look very, very good. This is a frog on frog's legs rather than a frog on stilts. And also it's grown it's grown antennae. Is that the word, antennae? So now what I'm going to show you is what it looks like during the training process. So this is a epoch 0. And then you have on the left is what it looks like when it's rendered. On the right is what the diffusion model is saying it should look like. So at the start, you can see that it generates some absolutely crazy images of frogs, and that's because the noise is quite high. But as you go on, you can see firstly that the frog is starting to look a bit more like a frog, but there are some problems with this. Here we go. So from this angle, when it generates the frog, firstly, it's a frog with two heads. And secondly, what should be the stilts there at the bottom, it thinks is a reflection, which is why it's generated these frog extra legs. because it thinks that that should be a reflection rather than the stilts. And I can go over more and more examples here. And also you've got like this frog has like a hat. And also it's the reason why I believe it has those weird antennae at the back with the sort of fake eyes on it is because when it generates an image from the back, it assumes that that's the frog's eyes from the back. So the multi-face Janus problem not quite been solved here. But as you can see, even though there are problems, it's still able to generate something. So that was 3 years ago. Has there been improvements? Yes, there have. There are models now called multi-view latent diffusion models, which can solve a lot of these problems, which maybe is another video in itself.
You're kind of talking about how to make random images effectively. How do we direct this?
So that's where the complexity starts ramping up, right? We've got a structure where we can train a network to produce random images, but it's not guided. There's no way of saying, I want a frog-rabbit hybrid, right? Which I've done, and it's very weird.